Noise is important in the quantum world because environmental factors can impact the computation. They can reduce the performance, they can reduce the precision. And so it's important to be able to filter out the noise. We announced a lower noise, that this next generation platform would also include lower noise technology. We said that this product would be available in the middle of next year, but that we would be incrementally rolling out the technology in our Leap cloud service over the coming year and a half. And to make good on that, last week we announced that in the cloud is a lower noise version of the 2000 qubit quantum computer. So using the new technology that we said would be in the next generation system, we fabricated our current system, and that's now available in Leap. So now when you go to Leap, you can run your problems on either the current product or the lower noise technology version of the product, and you can actually compare the results. So you can see for yourself the characteristics and the benefits of the lower noise technology. With the introduction of Leap, there are now thousands of developers that are using the system on a daily basis. In addition, we have over 40 paying customers that are developing applications on the system. And over 150 early applications have been developed to date. These are applications in everything from material simulation to optimization to machine learning to an eclectic mix of things like how to determine if there might be terror breaking out because of instability in a terrorist network environment. In fact, we have applications that have been developed for materials discovery, determining the electronic configuration of new molecules, being able to optimize the portfolio of fixed assets, which is very difficult to do because of the complexity and the need to do the analysis over multiple periods. This has been done on our quantum system. Antenna placement, vehicle routing. Volkswagen announced a while ago that they've solved a vehicle routing problem on our system, and they're moving toward putting that into production to optimize traffic flow across a metropolitan area. So a broad array of different types of applications. And we're just at the point where on the 2000 qubit system, we're able to see improvements in performance over classical on production size applications. Up until now, we've been able to see performance benefits, but on small applications because of the size of the problem that could actually fit on the quantum computer. But now, with some software advances, we're actually starting to see on production size problems that we can rival the classic approaches to solving these problems. And once we deliver the next generation processor with 5,000 qubits, we believe that we'll be ready to start more broadly moving applications into production. So with that, I'm going to actually show it to you. If we could switch over to my laptop. Okay, so if you were to go sign up for the Leap Quantum Application Environment and get to the login screen, this is what you see. Let me just log in. Okay, the first time you log in, you're going to get a set of recommendations of things that you should maybe go take a look at or try out. Learning materials, run demos, download and install the SDK to be able to build and submit your own applications. But basically, when you log in, you get your dashboard. Your dashboard tells you how much time you have remaining. So if you signed up for the free minute of time, there you see what's remaining. It gives you some interesting facts about the current system that's in use. The D-Wave 2000Q is online. It has 2038 active qubits, and it's currently running at about 14.5 millikelvin. That's the temperature. You also get your API token, which is what you'll use when you use the Ocean SDK to build apps and submit them to the system. You can upgrade to the minute per month by providing your Git address, or you could buy time on the system if you want to. We have a little what's new here, which is just saying that we've now introduced the low noise processor, and you can actually choose to run your applications on that as well. When you look at the solvers that are available to you, you'll see there are now two. One of them is the low noise processor. So let's go run a demo. The demo that I'm going to run is a social networking analysis demo. Basically, this is at its core a graph problem. It's a network imbalance graph problem. And essentially what the demo does is it talks a little bit about graph problems and the different types of things you can do by solving graph problems. And then it introduces the social networking problem. And we use Romeo and Juliet as an analogy for the social network imbalance problem. Basically, the structural imbalance problem or the social network imbalance problem is a graph partitioning problem. Think of a collection of entities, individuals or groups, connected by links that determine whether the relationship between the endpoints is friendly or unfriendly. So in the case of Romeo and Juliet, before Romeo met Juliet, it was possible to divide this network into two halves so that all of the friendly relationships were within one set or the other, and all of the unfriendly relationships crossed between the two sets. Now, turns out this is a very computationally intensive problem to solve on a large network. It's what's known as an NP-hard problem, and so the computation required grows exponentially in the size of the network. Okay, well, once Romeo met Juliet, it was no longer possible to divide the network in a balanced fashion. And the reason was, no matter which side of the network or of the river you put Juliet on, there was always going to be one link that violated the balance rule. So what's so interesting about the structural imbalance problem? What's interesting about it is that some work done both at Los Alamos Labs and at a couple of universities came up with the result that imbalance in a terrorist network is a predictor of violence. So if you've got a large terrorist network with friendly or unfriendly relationships between them, and it's not possible to divide the network in a way that it's balanced, that's a predictor of violence. And in fact, they analyzed the Syrian theater in 2012 and then again in 2013 and found that in 2013 the network became unbalanced and violence broke out. Well, what I'm going to do is I'm going to submit the 2013 network to the quantum computer. So it's actually submitting it directly to the quantum computer back in Vancouver, D-Wave headquarters. You can see that it took about 16 milliseconds to run the problem. It came back with 5 unique solutions, but none of them were able to be balanced. The imbalanced link in this solution is the dashed red line. So it's an unfriendly relationship in one of the two sets. Okay, so we've got a few different demos. Each demo is designed to help you get familiar with a different way of programming the D-Wave quantum computer. Okay, so maybe you've run through the demo or a collection of demos and you want to learn more, you want to get started with programming, so you can go launch Jupyter. We have one of the largest Jupyter Hub installations anywhere, all designed to allow you to learn more about how to code applications on the system. Here, we've got 5 notebooks. 2 of them are beginners. One of them is for factoring on the quantum computer, and the other one is for the structural imbalance problem that I just showed you. We've got a couple of others that are more sophisticated, including one that allows you to actually run a demo to see the advantages of the low noise, the new low noise processor over the older system. But just real quickly, I'll go to the Jupyter notebook for the structural imbalance problem. which is the one that we just ran. And here you'll see a detailed explanation of how you actually map the structural imbalance problem onto the quantum computer, along with the code associated with how you do all of that. You can go edit this code and submit it directly to the quantum system so that you have a quick start to actually writing applications on the quantum system, right? Alternatively, and let me just run back real quickly. Well, there we go. Okay, alternatively, what you can do is you can just go to Git and download the open source SDK, and there's full instructions on how to install it on your system, how to grab that API token that I showed you on the first screen and use it to actually start submitting applications. So as I said, every one of you can do this today. It takes about 30 seconds, you're up and running, and you're submitting applications to the quantum system. And then, of course, there's the community area, which is where you can go to ask questions or kind of communicate with your colleagues and start working together on problems. So just to recap, LEAP provides true real-time access to a quantum computer. And by real-time, we mean you submit your application, you get queued, you get the results back immediately. You don't have to pre-schedule time, you don't have to wait for us to run the problem for you. We have demos, reference examples, a full open source SDK. We encourage you to help us evolve the tool suite, and many of the developers that have signed up for LEAP are now helping us do that. And so it's really your time to learn how to program a quantum computer and to get started with the development. Thank you for your time.